Hello, I'm Simon Barner from Fortis Research Institute in Munich. In this tutorial, I would like to explain to you how model-based development of mixed criticality systems can be performed using the AutoFocus 3 toolset. I would like to start my presentation with a motivation for and a definition of mixed criticality systems. It is well known that nowadays innovation in embedded systems is at least in large parts based on software. This creates an increased demand for additional computational power. At the same time, embedded computer systems must become more efficient in terms of engineering, certification and production costs, but also with respect to other properties such as weight, space and energy consumption. As a consequence, more and more functions of different importance and criticality levels shall be integrated onto a shared computing platform. This results into the so-called Mixed Criticality Integration challenge. On the one hand, this challenge exists for the computer architecture that needs to provide mechanisms to safely segregate functions of different criticality levels from each other. In the DREAMS project, different mechanisms are defined in a waistline architecture that provides a set of core services based on which networked virtualized multi-core systems can be instantiated. On the other hand, the challenge also exists for the development process that needs to support the integration of the set of complex functions of different criticality levels onto the shared hardware-software platform. In this tutorial, I will demonstrate how seamless model-based development using the AutoFocus 3 toolset can help to mitigate this challenge. As a running example, I will use the integration of a safety critical function represented by an automatic cruise control system of a car with further non-critical functions such as an entertainment function. Before I start, I would like to give you a brief overview of AutoFocus. As mentioned, it is a model-based development environment for embedded systems that employs models at all levels of abstractions, ranging from the requirements to the logical and platform-independent system architecture over the platform architecture down to the deployment. It provides graphical views for modeling embedded systems as well as advanced design aid methods and technologies. AutoFocus 3 is an open-source Eclipse-based tool that is available online under the Apache license. After the requirements elicitation and the definition of the different functions of the systems, the next step in the development process is to decompose the different systems into subsystems. In the following, I will illustrate how this approach can be applied to the automatic cruise control example. At first, a component architecture is created. Then the interface of the system is specified. In the example, it consists of both sensor data such as the current speed and current distance, as well as user input to define, for instance, the mode of the ACC component, as well as the acceleration and the brake pedals. AutoFocus 3 has an extensible type system. In the example, an enumeration type is defined that is used to specify different operating modes of the ACC system. Based on the acquired input, the system computes the acceleration to set as well as a video signal to be displayed on the system's display. As mentioned before, the system consists of several components of different criticality levels, such as the adaptive cruise control component, as well as less or non-critical HMI components, such as the vehicle status aggregation component, as well as an entertainment component. Using directed channels, these components are then composed into a network of components. After the decomposition of the system into atomic component has finished, it is necessary to specify the behavior of the system. The first way provided by AutoFocus is the use of state automata. Here the transition conditions between the different states use the input ports of the containing components and produce during the actions that are triggered during a transition condition to write the output ports. In the example, the logic of the acceleration control is defined based on the mode selected by the user as well as the acceleration and the brake pedal. An alternative way to specify the behavior of a component is the use of mode automata. Here the component is decomposed into different modes. Transitions define the switching between the different modes. The behavior of a single mode is defined using embedded component architecture that is defined in the same way as it has been explained before. In the following, I will quickly show you how non-functional properties such as the safety integrity level or other non-functional properties such as the memory requirements of components can be annotated to the model.